So in this video, I'm going to take you through graphs of exponential functions. So just going to make a table for this equation, y equals 2 to the power of x, and probably easiest to start with 0. So when we plug in 2 to the 0, we get 1. Anything raised to the 0 power is 1. So now we're just going to plot that point, 0, 1, see what this function looks like. When we plug in 1, 2 to the power of 1 is 2. 2 to the power of 2 is 4, and 2 cubed is 8. So we can plot those points like this, and then 2 and 4, and 3 and 8, 5, 6, 7, 8. Okay, so we start to get this growth here, this kind of curving pattern. If we plug in these negative exponents, remember, those flip this around. So 2 to the minus 1 is 1 over 2, which is about exactly 0.5, and then 2 to the minus 2 is 1 over 2 squared, which is 1/4, or 0.25, and then 2 to the minus 3 is 1 over 2 to the third power, so 1/8, which is 0.125. So now the point of these is to see that, so -1, 0.5 is here, and -2, 0.25, is to see that these points are getting closer and closer to 0, but they will never reach 0. And so the curve will flatten out right here and never go below the x-axis. No matter how big I make this, if I do to the -100th power, that just means 1 over 2 to the 100th power, which does not equal 0. It's still a number that's greater than 0. So this is what our exponential function looks like. And notice the key of an exponential function is that the exponent is in the variable. So this would be exponential growth. From left to right, it's getting bigger. But this one, from left to right, it's going to be getting smaller. So when I plug in 0, we get 1 again. That's here. Plug in 1/2 to the first power is 1/2. 1/2 squared is 1/4. So it's actually getting smaller and smaller in this direction. But it's going to be getting bigger and bigger in the other direction. So 1/2 to the -1 means we flip the fraction. So that's 2. 1/2 to the -2 is actually 2 to the second power, so that's 4. And this is going to be 8. So we've got -1, 2, -2 and 4, and -3 and 8, 5, 6, 7, 8. Yeah, so then the curve looks like this. It's from left to right, it's actually getting smaller and smaller, and it will keep increasing in this direction. So this is exponential decay. And the key here, the difference is, if you look at the equations, the base, so if I write this in the form y equals b to the x, for exponential growth, b is greater than 1, and for exponential decay, b is less than 1. So are these growth or decay? And so again, we're just going to, for growth, the base has to be greater than 1. For decay, the base has to be less than 1. Oops, that should be a b. And maybe you're wondering, what if b equals 1? Well, if we raise 1 to the power of x, it's just equal to 1. So it would just be a horizontal line. It would not be an exponential function. So this one's going to be decay because 2/3 is less than 1. This is growth because 5/4 is greater than 1. And then these both are decay. So then we're going to graph some exponential functions. If we throw in this value, this is going to be our a value. So a times b to the x. And now to find the y-intercept of any function, we plug in 0 for x. And so then 3 to the power of 0 is 1, so we just get y equals 7 for the y-intercept. And remember, that's the point 0, 7. So 0 in the x direction, up 7, 2, 3, 4, 5, 6, 7. So there's the y-intercept. Now, is it growth or decay? Well, it's going to be growth because the base is greater than 1. Okay, so that means our function is going to look like this. Now sketch the graph, labeling the y-intercept. So there's the y-intercept. Now how do we get the rest of the graph? We just have to make a table of a few values. So already plugged in 0, plug in 1, and we get 3 to the power of 1 first, and then times 7, which is 21. So that's going to be way up here already after one unit increase. So then if we try -1, 3 to the power of -1 is 1/3, and then we multiply by 7, so we get 7/3, which is 2 1/3, so about 2.3, so 1, 2, so about here. So it's going to come down. Okay, and then it's never going to be equal to 0. It's just going to hover along this x-axis, just like this, because even if I raise this to bigger and bigger powers, like -100, we're going to do 3 to the power of -100, which is 1 over 3 to the 100th power, and then times 7. It's going to be a very small number, 0.00, and so on. But there will be something at the end of that. It will be greater than 0 still. So there's our sketch. Okay, another function. This time we're going to do decay, because this b value is less than 1. And if we find the y-intercept, we plug in 0. And we solve. This is going to be 1. And then we got this plus 4 outside. So the y-intercept is actually 5. 1, 2, 3, 4, 5. Okay, and then we know it's decay, so it's going to look like this. And then to get some more points on here, this 4 is actually going to become what's called an asymptote. So the graph is never going to go below this horizontal line right here at y equals 4 because of this 4 in the equation. So I know it's decay, it's going to go down and hover right at this, and it's going to go up in that direction. And I don't really even need any other points if I know that. I could plug in, like a -1, and see 1/3 to the -1 is equal to 3, because that just means reciprocal. And then when I add 4, I get 7. So -1 is up here at 7. So my graph's a little bit off, but that's okay. It's just this general shape. Sketch just means general shape. It doesn't have to be perfect. The key is to label this asymptote, which is kind of like an electric fence that the curve sort of gravitates towards, but it never touches, and then the y-intercept at 5. So that's about it for exponential functions. The key things here are being able to find the y-intercept, being able to identify if it's growth or decay. So growth, the base is greater than 1, decay, base is less than 1, and being able to make a sketch by making a table of values and just sort of knowing the general shape of growth versus decay.